All right, back to relations. So last time we talked about relations and their basic properties. And today we're going to be talking about two particularly special types of relations, which are equivalence relations and partial orders. And they're defined in different ways. So despite both being special cases of relations, we will find that they have very different flavor. So let's start with equivalence relations. An equivalence relation is a relation that satisfies a number of the properties we talked about yesterday. So it's, in particular, it is a relation that is reflexive, symmetric, and transitive. And we will see sort of why we call this an equivalence relation. And similarly, we call related elements, so elements that are related under this relation, are said to be equivalent. So let's look at some of the examples we saw last time. So for example, the less than relation is not an equivalence relation because it is not reflexive. Nor symmetric. In fact, the less than or equal to relation, as well as the divisibility relation, these are not symmetric and therefore not equivalence relations. The one example we did see last time, which was an equivalence relation, is congruence. So congruence mod 5, or mod anything, but just to make it concrete. Congruence mod 5 we saw is reflexive because something is congruent to itself. It is symmetric because congruence does not depend on the order. And it is transitive because if these two things are congruent and the second one is congruent to some third thing, then the first and the third thing are certainly congruent. So it is an equivalence relation. So equivalence relations are special essentially because of the following definition. So we can make this definition for any relation, but what's special about equivalence relations is that it works in a very nice way. So let R be a relation on a set A and choose an element A in our set A. Then define the equivalence class of little a is the set of B in A such that A, B is in R. Excuse me. So this is the set of elements in our set A that are related to little a. So in an equivalence relation, we say that related elements are equivalent, and the equivalence class of an element is just this collection of all the elements that are all equivalent to each other. And I should say it is denoted by putting brackets around A with an R to denote the relation, or if the relation is clear, just brackets. And it's useful to be able to go back and forth between thinking about the whole equivalence class and thinking about specific elements of the equivalence class. So an element of an equivalence class is called a representative of the class. So the idea is that an equivalence class, sometimes you want to treat it as a single unit, considering all the elements to be the same. And sometimes you want to pick a specific element and work with that guy. So that's the difference between a class and a representative of the class. So let's look at some examples with our good old congruence mod 5. So this is a relation on the set of integers. And one of the basic things that we learned when we were talking about congruence and modular arithmetic was that every integer is congruent mod 5 to exactly one of the following things: 0, basically 0 through n minus 1, right? So 0, 1, 2, 3, 4. So essentially what this is telling us is that in this case we have 5 equivalence classes. And these are representatives for each of the 5 equivalence classes. But let's write down kind of what the classes are. So the class of 0, and I'll put a little 5 to denote that we're working mod 5. The class of 0 is everything that is congruent to 0 mod 5. So minus 5, 0, 5, 10, etc. The class of 1 is everything that's congruent to 1, such as minus 4, 1, 6, 11, so on. The class of 2 is everything that is congruent to 2 mod 5, such as minus 3, 2, 7, 12, etc. And then I'll let you fill in the rest. But the equivalent class of 3 and of 4 are basically similar things. So this is a first example of an equivalence relation. And I said that equivalence relations are special because they make equivalence classes work properly. So let's talk a little bit more about that. Let's be more precise about what we mean by that. So essentially what we mean is a more general analog of what we're saying up here. So be lazy and write dots for a 5-element set. So this statement, that every integer is congruent to exactly one of these numbers, reflects the following general property. Let's have a theorem. Say we're dealing with an equivalence relation. In an equivalence relation, every pair of classes are either equal or disjoint. So any two equivalence classes are either equal or disjoint. Furthermore, every element of the set is contained in exactly one equivalence class. So let's revisit our definition of equivalence classes very quickly. So let me not give an example, but just to say, you can apply this definition to any relation. We didn't assume anything about the relation to say this. But if you choose something that is not an equivalence relation, then you will find all sorts of strange things happening. Like for example, if your relation is not reflexive, the element A might not be in the equivalence class of A, which is a very strange thing that you want to rule out. Or you might have A is in the equivalence class of B, but B is not in the equivalence class of A. Another very strange thing that can happen for relations in general, but we want to rule this out if we're considering these elements to be equivalent. Right? So this theorem is basically saying that equivalence classes work very nicely. And this is why we're interested in equivalence relations. So let's go ahead and prove it. All right, let me look at my notes. How do we prove this? So we want to take two equivalence classes and show that they are either equal or disjoint. So the approach that we're going to take is let equivalence class of A. So here, let's let A and B be elements of our set. And suppose their equivalence classes are not disjoint. So we want to show that they are equal. Because we're claiming that they're either equal or disjoint. So that's the same as saying that if they're not disjoint, they must be equal. So this basically comes down to using symmetry and transitivity. So these are two of the defining principles of an equivalence relation. So we're supposing they're not disjoint, which means the intersection is not empty. So we're going to take an element in the intersection and use it to relate these two equivalence classes. So let C be an element of equivalence class of A intersect equivalence class of B. So that is to say that C is related to A and C is related to B. So I mentioned this notation before. I didn't use it much, but I'm finding it convenient to use in this proof. So remember that this just means that the pair CA is contained in R, or again in words, that C is related to A. So having something in an intersection just means that it's related to A and it's related to B. And by symmetry, we can flip this around. Let's flip this around. By symmetry, we can flip this around and say that, oh, I'm looking at my notes and confusing myself, because I think if I want to be very precise, I wrote this backwards. It doesn't matter for equivalence relations, happily, but just to be very precise in our proof, let's write it the right way around. So this means that A is related to C, is what it means to be in the equivalence class of A, and B is related to C as well. Okay, now I think we are back on track. By symmetry, we can flip this guy around, which is to say that B is related to C. C is related to B. Excuse all of my typos. So by symmetry, we can flip this thing around. Get that? And by transitivity, we can combine this thing and this thing to see that A is related to B. So this is the start of connecting these two equivalence relations. And now essentially we just use transitivity to complete that. So let D be any element in the equivalence class of B, which is to say that B is related to B. Then combining these two by transitivity, we see that A is related to D. Which is to say that D is in the equivalence class of A. So what did we just do there? We took any element of the equivalence class of B, and we showed that it is in the equivalence class of A. So what that shows is that the equivalence class of B is contained in the equivalence class of A. And there was nothing special about the order. So, or by symmetry, we can reverse the order everywhere. So same argument. Shows that the equivalence class of A is contained in the equivalence class of B. And having shown the inclusions in both directions, we conclude that they are equal. And that is what we wanted to show. So that's the first part of our theorem. Let's bring the statement back here. In an equivalence relation, any two equivalence classes are either equal or disjoint. So we have proven this. And further, every element is contained in exactly one equivalence class. So to prove this, well, let me leave that up on the screen. To prove the second part, we've already shown, since the equivalence class of A and B is either equal or disjoint, that shows every element is contained in at most one equivalence class. Since the intersection of distinct ones is empty, to see that it's exactly one, you will notice that we have not used reflexivity yet, which is our third defining property of an equivalence relation. So here's where we use it. By reflexivity, A is contained in the equivalence relation of A, and that shows that it is contained in some equivalence class. So it is contained in exactly one. And that completes our proof. So another way of stating this theorem is to say that in an equivalence relation, the equivalence classes form a partition of our set. And what does this mean? What is a partition? A partition is a collection of disjoint subsets whose union is the whole set. So a partition essentially means that you have split your set up into, basically you have partitioned it off into disjoint subsets. And in fact, I won't prove this, but you can work it out if you want. It's a good exercise. To give an equivalence relation on a set A is actually the same as giving a partition of that set. And the connection is essentially that the equivalence classes are the partition. This allows you to go back and forth. So let's finish with talking about some of the things we know about modular arithmetic from this new perspective. So let's rephrase some modular arithmetic. Define Z mod M. So remember, we defined this before to be the set 0 through m minus 1. But we can redefine this to be the set of equivalence classes of congruence mod M. So we showed that this gives an equivalence relation on the integers. So we can consider the set of equivalence classes. And because of what we were saying before, that every element belongs to exactly one equivalence class, and that every element belongs to exactly, is congruent to exactly one of the numbers 0 through m minus 1, this is essentially the same as what we said before, but phrased in this more flexible language. And indeed, this is sort of how you would generalize these types of ideas if you were going to start doing more abstract algebra. And we have this, wow, we have this natural map from the integers to Z mod M. And now we can just write this as element of the integers maps to the equivalence class of that element. So as you can see, this is a very clean way to write this theory. And some of the facts that we proved about addition and multiplication, this is no longer sort of a set of numbers, it's a set of sets of numbers, it's a set of equivalence classes, but we can define addition and multiplication by class of A plus class of B is defined to be the class of A plus B. And we showed, so this is not obvious, but we did show that this is well defined meaning it does not depend. So in order to make this definition, we had to sort of choose representatives of these equivalence classes. So when we write A plus B, we've chosen representatives of each of these two equivalence classes to add together. So you need to show, which we did essentially before, that it doesn't depend on the choice of representatives. So if you choose a different A and you choose a different B, then A plus B might well be different, but the equivalence class of A plus B will remain the same. So equivalence classes and equivalence relations are extremely useful for thinking about a lot of different things. And this is a good example. Modular arithmetic is something that generalizes to a wide number of different situations. And the way you think about it in general is in this language of equivalence relations and equivalence classes.